Hi guys, welcome back. So we're going to be talking about our second virtual lab video again. And again, this is the molecular structure and shapes. And once more, I am Dr. Nanette K. Hartley. So let's go ahead and talk about molecular structure and shapes. Now, I love talking about this because if you're tired of math, we're moving to something completely different. So we're going to be doing something that is not really based in math. This is much more based in your ability to see things in 3 dimensions. This is a great preparation for moving into organic chemistry. And if you're not so great with the math stuff, all you have to be able to do here is add and subtract. So this is a very different set of math skills. It's a good change, especially at this time in this term. So let's talk about how this works. Now, our objective in doing this experiment is to observe the building of molecular examples using ball and stick virtual models. So we are going to have some ball and sticks that we can work with in this virtual environment to actually build examples of molecules. And then we're going to be able to pick them up and turn them around and look at them in all different kinds of ways so that we can see what they look like. And once we've done that, we'll be able to use those to observe the three-dimensional shape of those molecules. And from those observations, we should be able to predict the electron pair geometry. So what this thing would look like if all of those things that were on there are described. So the electron pairs as well as the atoms. And then the molecular geometry. So if only the atoms were being described. So not the electron pairs, but only the atoms. Okay, so that's the difference between those two things. In one case, we consider everything that's around the center. In the other case, we only consider the atoms that are around the center, but we consider them based on where those electron pairs are as well. So what are we going to need to do that? Well, that's a good question. We have to be able to draw a Lewis dot structure to be able to do this. We need to correctly identify that Lewis dot structure to be able to look at the geometry, because I need to know if there are lone pairs. If those lone pairs are there and I don't take them into account, then that affects the geometry that I should be seeing. So I need to know how to, 1, draw one, and 2, check to make sure it's the best structure. I also have to learn how to use a table to determine the electron pair geometry and the molecular geometry once I have that correct Lewis dot structure. So that's the important background that I need. So I know how to draw a Lewis dot structure. Well, you're probably pretty new at this. So let's talk about what the steps are in doing it. This is what we've been talking about in lecture fairly recently. So my steps for drawing Lewis dot structures, this is what I tell my students. It's a 6-step process. The first thing we do is we take and we look at the formula for the molecule that we're trying to draw. And we sum the valence electrons from all the atoms in that formula. And then we add additional electrons if there's a charge, or we take them away if it's a positive charge. So if it's a negative charge, we add them. If it's a positive charge, we subtract, take them out. Okay. We write the symbols for each atom. So if I have a particular molecule that I have, that first thing that's shown typically goes in the middle, and then we draw all of the other stuff around it. Okay, so that's my base structure. And then we connect all of those things by drawing lines between them or drawing 2 dots between them, and that is that bond, because everything has to be connected by a bond. Each bond takes up 2 electrons. So then I have to count the number of electrons that we took up with the bonds and subtract that from the total. The next thing I do is my exterior atoms. I need to fulfill their octets. So everybody has to have access to 8 electrons. We want that octet structure. So we fulfill the octets on the outside and then subtract all of the electrons that I used to make that happen. And if there are any electrons left over, whatever count of electrons I have left, those go on the central atom. Now there may not be any left, and that's okay. If there are some left, we put those on the central atom. Now, if I get to this point and there aren't enough electrons on my central atom, then I need to start making double bonds. We don't make double bonds unless we don't have enough electrons on the central atom. Okay. And now I need to look at the very end of that. I need to calculate a formal charge for everything in that molecule. So every single atom that's in there, the center, all the guys on the outside, we need to calculate a formal charge for them. And a formal charge is described like looking at the number of valence electrons that atom brought to this. So how many electrons did it bring to the party? We subtract the number of bonds that it has. So how many bonds does it make? And then we subtract the number of non-bonding electrons. So how many electrons does it have around it that belong only to it? Okay, so the number of non-bonding electrons. So those are my steps. Okay, awesome. Steps. Cool. Let me close this out. Now I wrote all of that down, not necessarily the easiest thing to read, but those are my steps. Okay. So that's my process that I'm going to go through when I deal with this. Okay. Now the only other thing I have here is a periodic table, because I might need to look at that while I'm dealing with this. And I want to walk through one example of how we draw a Lewis dot structure so that we're extremely clear on how that happens. And I want to make sure that it's a good one to look at. So I decided that we were going to work on XeF4 because I think this is a good one for us to look at. So XeF4. So the first thing I want to do is sum all of the valence electrons that come with this. So I know I have one Xe that's in this, and I have 4 Fs. So 1 Xe, and so I'm going to multiply by the number of valence electrons there, and I have 4 Fs, and I'll multiply by the number of valence electrons there. So how do we count valence electrons again? Well, my valence electrons are the ones in the outermost shell. So the ones that come from the S block and the P block, because remember, these D's and these F's are actually inside of that. So they're in N-1 and N-2. So those are not outermost shell. So we don't count those. We only count the ones that are in the S and in the P. So if I'm talking about Xe, he's over here. He's a noble gas. So in my S block, he's got 1 and 2. So 2 in the S. And then I want to come over here and look at P block. I'm going to highlight the P block so that it's easier for me to look at that. So he's in this row right here. So he's got 2 in that S, and then 1, 2, 3, 4, 5, 6 in the P. So a total of 8 electrons that he brings to the valence shell. So that's a total of 8 that we get from that Xe. Okay, and I know that because he's all the way over on the side. So I know that that group over there, that's 8. Okay. Now Fe is right here. He's a halogen. And all of my halogens are 1 less electron than this group right here. And so knowing that there are 2 in the P block, we have 1, 2, 3, 4, 5 for a total of 7 in my halogens. So 4 times 7 is 28. And that means I have a total of 36 electrons that I have brought from these components that I have in this particular molecule. Okay, so that's what I have from those. Now I can make this small. It can go away. And I know how many valence electrons I have brought from each of these components because I wrote them right here. So when I go to do the formal charge, I have that. Now I know the total number of electrons that I have to put in this. And I know the formula, so I know where everything should go. So first thing written should be this thing in the center. So Xe is going to go in the middle. I have 4 Fe's, so I'm going to write them around the outside. Doesn't really matter where I put them. I have a natural tendency to put them at, as far away as I can get them from each other. So I've now got these 4 guys around it, and I know I have to connect them. There has to be a bond. So I'm going to draw a bond here, a bond here, a bond here, and I'll draw the dots here because not everybody likes to draw the lines. It doesn't matter which one you do. They're equivalent. So this line is 2 electrons. So 2, 4, 6, and 7, 8, because there are 2 in there. So that's 8 electrons that I drew. So I subtract 8, because now I've taken up 8 of my total electrons by drawing those bonds. And actually, I wanted to do something, change. Sorry, I meant to do something. There we go. So there, 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 and there. So I subtract those 8. Those were in the bonds. And that then leaves me with 28 additional electrons that I have to work with. Okay, so I've taken out all of the electrons in the bonds. That leaves me with 28 that are left. Now, what's the next thing I do? 3 says complete the octet on the outside atoms and subtract the electrons from the total. So now I'm going to the outside atoms. So I'm going to switch to a different color. I want to do the octets on the outside atoms. So now I'm looking at these guys on the outside. So I'm going to do fill the octets. So he's got access to 2 electrons right there. So I draw 3, 4, 5, 6, and 7, 8. I'm going to do that for all of these. Okay, so I'm going to add 6 electrons to the rest of these. 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. And some people count as they go. So 6, 12, 18, and 24. And that leaves me with 4 electrons. And this is the outer octet. I just like to label what I've done and where I did them. So where did those electrons go? This is how I like to do my stuff. I don't always do it in bright, colorful ways, but there you go. So now I change to another color just because I want to know where these go. So I've got these 4 electrons that are left over. Where do I put those? Put any leftover electrons in number 4. Put any leftover electrons on the central atom. So I've got 4 left. I'm going to put 1, 2, because I have to go in pairs, and then 3, 4. Doesn't matter where I put them, as long as they're not where a bond is. That's all that matters. So I've put them there. I then used 4 electrons, and they're all gone. So I've now accounted for all of the electrons that needed to be there. Cool, that's awesome. There's one more thing that I need to do. And so what I need to do here is I need to come up here and I need to calculate the formal charge. So I'm going to do the formal charge for Xe, and I'm going to do the formal charge for F. And because they all look the same, all of the F's, they'll all have the same formal charge. And the first thing I want to do is the valence electrons. Then I'm going to subtract the number of bonds, and then I'm going to subtract the number of non-bonding electrons. So we're going to do D, and I'm actually going to do, just because I like to be obnoxious, it's the bonds and the non-bonding electrons. Okay, so my valence electrons, for Xe, I have 8 of them. So for Xe, this is 8. For fluorine, there are 7. Then I am going to subtract the number of bonds. Now, my number of bonds for my Xe, I have 1, 2, 3, 4. And then when I look at the number of non-bonds, I have 2 pairs that are sitting on there. So 1, 2, 3, 4. 4 electrons that are sitting on him. And so 8 minus 4 is 0. So his formal charge is 0. Okay. When we look at fluorine, we have 7 valence electrons that we brought to this party. I subtract the number of bonds. Each one has 1 bond. So there's one bond for each fluorine. And then I want to count how many non-bonding electrons there are. So 1, 2, 3, 4, 5, 6. And that means that that is also a zero charge. So since I have no charge on that one too, and I didn't change colors, but since I have no charge on that one too, that means everybody has a zero charge. Since there's a zero charge everywhere, I don't have to change anything. And this is the formal structure that I want. Okay? No formal charge anywhere. This is the structure that I'm looking for. I move things up a little bit. Why did I do that? Because I wanted some space. So what I have is 4 bonds on my central atom. I had 4 bonds, 1, 2, 3, 4, and then 2 non-bonding pairs. 2 non-bonding pairs. Okay, well, that's awesome. Now, I'm not in the lab yet. So what I'm going to do is I'm going to come back here and I'm going to look at this one and I'm going to pull up my D2L because in my shell, I know that I have my exam handouts that my instructor gave me. And I know that in those exam handouts, I have a copy of this table that we will get a version of in lab. And that looks like this. So I can zoom in on this a little bit. That will make my life easier. What it says is the number of bonding groups and the number of lone pairs. So I want to find where I have 4 bonds and 2 lone pairs. So I see 4 here, but that's 0. I see 4 here, and that's 1. And if I look all the way down here, I have 4 and 2. My example molecule is XeF4. Oh, look, isn't that nice? The electron pair geometry is the first thing. The molecular geometry is the second. So I'm going to write electron pair geometry here. Oh, hold on. Move this over so we can look at that. And then the molecular geometry. So again, with my electron pair geometry, I'm taking into account everything that I drew. So it takes into account these 4 bonds and the 2 lone pairs. So if I look at my table, it says that if I take all of that into account, that's an octahedral structure. And what that means is I would be taking into account all of this stuff. So the 4 around the plane and the 1 up and the 1 down. So all of that. So that's called an octahedron. So that's an octahedral structure. And when I only consider the bonds, these 4 bonds, because they are going to exist in the plane, the biggest separation I could get between those lone pairs is to put them on opposite sides so that one's up and one's down. That means that the 4 that are left are all in the plane. So they're 90 degrees apart in the plane. Then that's going to be called square planar. So that's the structure that I'm looking at. And all I have to do is look at the table for how many bonds I have, how many non-bonding pairs, look at the column that says electron pair geometry to get the electron pair geometry, and then the molecular geometry to get the molecular geometry. Now, if it asks me for the structure, I'm looking for the molecular geometry as well. Okay, so those terms are synonymous. So that's what I'm going to be doing. Cool. My Alex did time out, so bummer. I'm gonna have to fix that. I'm gonna close this first. And I'm gonna come back so that we can get into Alex. I'm gonna show you one of these, just so you understand where the pain point is in doing. Get this all set up, but it took me too long to get to it. Heck. Helps if I remember to go to the student view. And I need to go into my assignments. Close my exam 1, my exam 2, my exam 3, and now in the virtual labs, we want to go here. Darn it. Give me just a minute. Give me just a minute, I'll be right back. Much better. Now I have a molecular structure and shapes that I can get into. So we'll open this and we'll start this. And all this tells you is that we're going to be looking at this. In this simulation, we'll use the Lewis structures and the Vesper theory to predict this. We're going to score this. This is our molecular model kit. So this is how we're going to work this. Green for chlorine, blue for nitrogen, red for oxygen, black for carbon, and white for hydrogen. We have light blue for multiple bonds, white for single bonds. The 3D models will be placed on a plastic stand, and then you'll view the geometry table. And so this is the geometry table they're going to ask you to work with. So it's not quite the same as what we give you in class. It's a simplified version of that. Okay. So we can close that and we can go to the simulation. Now, it asks you a question about this. I'm going to skip this part. Okay. So we want to select the central atom to place on a lab bench. Now, it says I'm doing CH2Cl2, but I don't remember what it said about what was what. So I can show the labels. So I need a carbon. I need 2 hydrogens. And I need 2 chlorines. So if you forget what things are, you can remember to do that. And then I need single bonds. 1, 2, 3, 4 to do that. I place a central atom on the stand. That's this one. I do single bonds. Randomly connect them up there because it puts them where it wants them. And then I want to put a terminal on there. Doesn't matter where I put them. And then identify number of bonding groups around central atom and record in the lab data. And I do this, and I want to go and do the electron geometry. And I can't. And it says click completed structure to rotate. So I gotta close this. And I gotta come out here and pick this thing up. And what it wants me to do is move this around so I can look at it. And I want to be able to rotate this so I can look at it in all kinds of different directions to see what it actually looks like. This is what they want you to do. Now, are you required to do that? No. All you gotta do is move it. Wait for it to render and move it. That's all you really have to do. But it's important that you understand what it looks like so that you can try and understand why they have the names that they have. The easier if you can remember them for a reason. Now you can close this and you have to determine the geometry. So you need to come into the lab data and how to draw a Lewis structure. This is the instructions on how to draw it. How to determine. This is how you determine it. And this is the geometry table. So we had 4 bonds, no lone pairs, 4 bonds, number of groups that are in the central 4, no lone pairs. That is a tetrahedral electron pair geometry and a tetrahedral molecular geometry. Okay? So what happens when you do these is they'll have the same electron pair geometry, but if you change the number of lone pairs, it changes the molecular geometry. Okay, so that's what happens. So tetrahedral will go here, and our molecular geometry is also tetrahedral. And so that's what I wanted you to see, is that you need to make sure to click this and render this structure and turn around so that you can do that. And that will get you to the next page. So that's all I'm going to show you, is how to do that first one. So that should take you through the rest of this. You will need to do all of these and make sure that you answer all of the questions. So that's what you needed to see for this particular one. So I hope nobody has any questions about any of this. If you do, please feel free to reach out to me or one of the instructors. We'll be happy to help you with this. And that should be good. Thanks, guys. I'll talk to you later.